All right. Hello, honors group. So, reminder our exam is on Wednesday. So, the exam will be Wednesday. After your third period exam, you'll have your fourth period exam. If you have lunch fourth period, reminder you do not have to stay for that period. You can actually go home. So, you probably want to start thinking about how am I getting to school to and from on exam week, because the buses are going to run normal schedule. So I don't know if you want to hang out there till 2:30. So with Friday, so on Friday we went over all the big major topic ideas, the big takeaways that you want to be able to know and take from there. Something super specific like me asking the density of water, that's not going to be on there. So don't focus too much about like really teeny tiny nitpicky things. Think big concepts, big ideas that we've gone over this past semester. Reminder, you do get that note card, so you have that note card available to you to utilize. So with motion, remember on Friday we had said, know an object is in motion if its position changes. So as long as you are sitting still, if I compare that to the desk that you're at, you're not moving, but I could pick something else. So I could pick the moon and then all of a sudden you are moving. So technically, remember we said everything is always in motion, but typically we describe motion as actually moving your body, moving yourself, or moving a car. A parked car we would not typically say is moving, even though in the scientific sense, if we pick a different stationary object, then yes, technically it can be moving. We then talked about distance and displacement. Reminder, distance is that total path. You take every single leg, you add it all together. Whereas displacement, we're only looking at your change in your position. So final minus initial. Okay. So on the picture, if you look starting at home, when they walk to A, they cover a distance of 0.5. When they walk back to B, they cover another distance of 0.5. So that's where you're going to get that total distance at B of 1 kilometer. But remember, if you leave somewhere and come back to the same spot, your displacement is going to be 0. If you notice with displacement, I included east or west for some of my designations because those are my directions for where the person was walking. So every part of that trip, each leg, you just need to add all those legs together to get the total distance. So when you walk from home to A to B to C and back to D, that total distance is going to be that 3.75 kilometers. Whereas I would want to see where did I start versus where did I end. So there's X final. Here's my X initial. How far is that? All right. So we're able to kind of work backwards. We know that this chunk here is 1 kilometer. So if the whole thing's 1.75, this little bit must be 0.75 kilometers. We then progressed on to looking at speed and velocity. Speed and velocity, if I go in a straight line, are going to be the same value. But if I don't go in a straight line, then they're going to be different. I calculate speed by taking distance divided by time. So on the graph, if you look, I kind of broke each of those points into different chunks. So from A to B, they walked 6 meters. From B to C, they walked a total of 3 meters. C to D, they're standing in the exact same spot, so 0 meters. D, they walk a distance of 5 meters. So when you're taking the exam, what I would suggest is break that into those different segments. So then you can say, okay, well, what is the distance total? What is the total displacement from start to end? If I ask for a specific spot where I just want the speed or just velocity, then really we're calculating and solving for slope with those graphs. The graphs are the one thing I would definitely put on your cheat sheet just so that you have a reference back. Okay, that was all the way back in January when we did those graphs. Now, worst case scenario, could you just read your graph like here looking at C, coming to the left and saying, hey, I'm at position 9. And then at D, hey, I'm still at position 9, and connect that together and say, okay, what does that mean? If I'm at position 9 and I'm still at position 9, oh, that means I did not move. So worst case scenario, you don't have to memorize it, but you can just kind of read that y-axis, okay? Having it on your cheat sheet, though, might give you a little bit of comfort going into the exam, but just something to consider. So those calculations are there for you on the left, so definitely double check those numbers. Then we looked at motion diagrams, and we brought this idea back on Friday. And remember, if the distance between each of those snapshots, the dot represents the snapshots. If the distance between them are the same, boom, 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 then they're going at a constant speed or a constant velocity. On a position time graph, remember that's just a nice linear line. So that means it's not going to accelerate. Whereas if I zoom down just a little bit, these bottom two, if you notice, do have an acceleration. So on position time graphs, when there is an acceleration, you will see the line actually curve because it's either speeding up or it's slowing down. On velocity time graphs, if I have a horizontal line, that means my slope is 0. That doesn't mean that I'm stopped. It just means that I'm going at the same velocity or the same speed for a long period of time. If I get a linear line, like these two down here, where the line's going up with a positive slope, that means I'm speeding up. Or with a negative slope like that one, it means I'm slowing down. Okay, so go ahead. I'm going to zoom in just a little bit so you can go through and double check those ones really quick. All right, so remember on that position time graphs, our slope is equivalent to velocity. So if I said, hey, can you solve for the velocity, or hey, can you solve for the speed, you would just really need to use the positions on that graph and calculate the slope. The steeper the slope, remember, the faster the runner or the faster the car is going. And then if I have a slope that's equal to 0, ask yourself, well, why is it 0? Is it because my position isn't changing? Or is it 0 because my velocity isn't changing? If my position isn't changing, then I'm stopped. If my velocity isn't changing, that just means I'm going at a constant speed. Okay? So you gotta be really, really careful, especially on this next one that you see here. I need to look at my y-axis first and say, okay, at this point A, at time 0, I'm going 0 meters per second. At B, 2 seconds later, I'm going 20 meters per second. So that means I have sped up. And so you can calculate the acceleration for that segment, which is what's happening over here. And I put that note there. All I'm doing is asking for you to calculate the slope. Okay? Since it is acceleration, I did include positive and negative values so that I would be able to indicate that vector quantity. All right, on to forces. So remember, inertia is a property of matter. All things that are made of matter. So not heat, not light, not sound, but everything else in the world has inertia. Remember, the larger the object is, the more massive it is, the harder it is to change their motion. So it's not that semis can't go fast. It's just semis take a long time to speed up, and semis take a very long time to slow down. Okay, so with those forces, we had balanced and unbalanced forces. We know that if the forces are balanced, net force is 0, means they're going either at a constant velocity or they're at rest because there is no acceleration, because that relates back to F net equals ma. Well, if F net's 0, it's not mass that's 0, it has to be A that is also 0, right? If it's unbalanced, the object can speed up and can slow down because F net equals ma. If I have a value for F net, then I have a value for the acceleration. Okay? You should feel pretty comfortable looking at free body diagrams. Are they balanced? Are they not? If you have forces up and down that are the exact same magnitude, so the same number, they're going to cancel each other out. If those two values are different, they are not going to cancel each other out. And that means there will be a net force, and our object is going to accelerate in the direction of the net force. Okay? So, for example, on this one, if I look up and down, my forces are balanced. I have a positive 20 up and a negative 20 down. Those will cancel each other out. So that means in the y direction, the object is not going to accelerate. But then I need to look and see my x direction. I have friction to the left and nothing to the right. So there's no force canceling out that friction. Left is typically negative, so if you notice I wrote negative 60 newtons or 60 newtons to the left for the net force. Since it's friction, remember friction opposes motion. So since friction is to the left, I know the object is moving to the right. So this is probably a coasting car. And so if you remember the idea of coasting, a coasting car will eventually slow down because we have friction acting on it. So that's going to cause us to have a negative acceleration. 14, object A has a mass of 10 kilograms, object B has a mass of 25. If they have different masses, remember the larger the mass, the greater the force needed in order to get it to accelerate. So if I push on them with the exact same force, that object A is going to accelerate a little bit more. We solve with F net equals ma, mass times acceleration. That was Newton's second law. Newton's third law is what we have here in 17, where we have for every action, there's an equal and opposite reaction. So for every action, there's an equal and opposite reaction. So remember, we always said the bat hits the ball also hits the bat. And then I always ask you, well, hey, which force is greater? And everybody always tells me the bat hitting the ball is greater because the ball goes flying. Remember, the forces are equal, but the result of those forces is not going to be the same. Because me holding a bat has a lot more mass than that small baseball. The small baseball has less mass, so it has less inertia, so it's going to go flying away. Whereas me and my bat are not going to go flying away. Okay? Reminder, acceleration here on Earth, 9.8 meters per second squared. So if I drop two objects of different masses, they accelerate at the same rate. They hit at the same time. But if they have different shapes, like a feather and the hammer in 19, obviously that does factor in air resistance. So if there is air resistance, then unfortunately, we won't only have gravity pulling the objects down. If I have no air resistance, though, they should strike at the same time. All right, work and energy. Remember, kinetic energy is 1/2 mv squared. Potential is mgh. So based upon what is in the equation, if I increase mass or increase velocity, that increases kinetic. Whereas potential, I can increase the mass, gravity, or the height. Now here on Earth, gravity is always 9.8 meters per second squared for the acceleration. So that one isn't quite going to be something I can control unless if I go to a different location. Remember, energy cannot be created nor destroyed. So when I look at this pendulum, I am going to zoom in for you so you guys can double check right now. I have potential and kinetic constantly being transferred back and forth to each other. So at first I had all potential when I pulled the actual wrecking ball up or the pendulum up to position A. And then once I let go, the height decreases. So as that height decreases, you notice the potential energy goes down till eventually where I'm not elevated above that initial position, D, anymore. So I have all kinetic at D, going the fastest. And then once I pass D, I start to go up and go above that initial position. So more height gives me more potential. And then eventually it's going to turn back around and come this way. And it'll just keep going back and forth, back and forth, back and forth. Now a perfect pendulum would keep swinging forever and ever and ever and ever. Unfortunately, there is air resistance. So that's going to eventually cause it to slow down and won't return back to its extreme highest position at A or G. Same deal over here. If I take a look at the ball as it rolls down the inclined plane, no matter what, my total mechanical energy is always 100%. We did this with a lab where the potential energy at the top should be equal to the kinetic energy at the bottom, because all of the potential at the top gets transferred into kinetic energy at the bottom. Halfway down, you're going to notice I have 50% potential now, so then the other 50% has to be kinetic. No matter what, total energy always needs to add back up to 100. So with 23, you guys can see there's all the numbers for the answers there. We should see the energy totaling up to 2,000 joules no matter what. Now in real life, is it always going to add up to be 2,000? Probably not, because we do have friction. So since there's some friction, the potential energy at the top is going to always be a little bit bigger than the kinetic energy at the bottom. Okay. 25, 26, we have some calculations. 1/2 mv squared. Don't forget, velocity here does get squared. Potential energy, mgh. Don't forget, G is 9.8. So you got your different values. Remember, work and energy is measured in joules. Excuse my dog, I'm sorry. And then we finished that unit. Remember talking about work. We said if there's net work, if there is a displacement, work has been done. If there's no net force or no displacement, then no work. So even though I can hold a dumbbell above my head and it feels like my muscles are screaming at me that it hurts, that, oh my gosh, I can't hold this forever and ever and ever. If I don't move it, then technically I'm not doing any work in the physics sense. Okay? Thermal energy, remember we spent a decent amount of time going through what's the difference between heat and temperature. Heat is a type of energy. It is thermal energy, whereas temperature is a measure of how hot or cold something is, how fast those particles are moving. So the faster moving particles, like a gas, had higher temperatures, whereas solids who just vibrate in place and they don't move very much had lower temperatures. As you started going through that, we said heat is exchanged when two objects are in contact. If they're in contact and they're different temperatures, then we'll have heat constantly being transferred till eventually they reach the same temperature. We had conduction, convection, radiation as our three modes of energy transferring. Remember, radiation was the only one that could happen out in space. Convection was with our fluids and gases based upon density differences. So hot things rise because they are less dense. Cold things fall because they are more dense. And then the conduction was the direct contact between two objects. Then we went into specific heat, which that kind of ties in here with that FET. Remember, specific heat is how much energy do I have to add in order to raise the temperature of my material. So there is a couple things that factored in with specific heat and how much energy I had to add. If you remember this equation, Q equals MC delta T. Well, if I want to raise the temperature a lot, then I need a lot of heat. If I have a large body of water, then that's going to take a lot of heat to heat up. And then that final characteristic, that C in the middle, was our specific heat. So specific heat was C. And we said if I had a low specific heat, I was a conductor. If I had a high specific heat, I was an insulator. Okay. Remember, metals are good, not only electrical conductors, but also thermal conductors, so they heat up quickly. That's why we make our baking pans out of metal. Whereas something like water is a good thermal insulator. So that means it takes a long time to heat up and a long time to slow down. And then we got into our two units that should be the most familiar to you, and that's waves and electricity. So waves, remember, were a disturbance that can move through space or matter. We had different types of waves. We had mechanical that require a medium. Electromagnetic do not require a medium. We had how the particles actually move, whether they move perpendicular with transverse or if they move parallel with longitudinal. We said if they require a medium like sound, mechanical waves, then they're going to travel fastest in a solid. Electromagnetic waves, though, travel fastest in a vacuum because they don't want to actually travel through any medium. Even though they can, they don't travel that fast through them. Remember, we identified different parts of the wave. Amplitude is our height. We measure that from rest to crest or rest to trough. Or during our lab when we went outside, we did crest to trough and then divided it by 2. So you can solve for that in a variety of ways. One thing that you definitely want to go back over and refresh on are our different wave interactions. So refraction, that's where the actual pencil looks broken or the straw looks broken because the wave gets bent. Reflection is the bouncing back of a wave. We talked about echolocation, sonar, echoes. Diffraction, this was the cheerleader megaphone, or why people can hear me in the hall even though they can't see me. It's because the wave bends as it passes through a small gap or around a barrier. Interference, when sound combines or when waves combine, they make a bigger wave or they cancel each other out. There's 2 types, the constructive and destructive. And then that Doppler effect, which is the apparent change in frequency because the source is moving. So the ambulance, as it comes closer to you, sounds higher pitch, and it's going to sound higher pitch because the waves bunch up. And so you get a higher frequency. When the ambulance passes you, the waves can spread out, and so then you get a lower frequency, lower pitch. And then our absolute newest unit, which was electricity. Remember, with electricity, we had V equals IR. V is voltage, I is current, R is resistance. Voltage measured in volts, current measured in amps, resistance measured in ohms. Remember, resistance, there's a couple ways to change the resistance. Longer the wire, that has higher resistance. Thinner the wire, that has higher resistance. And then also, depending upon the type of material it is, it could have more or less resistance. If it is a bad conductor, then it has more resistance than, say, copper, who is a good conductor. Okay? Electrons flow, remember, from the positive to the negative to the positive terminal, because electrons, opposites attract, likes repel. So they want to get away from that negative terminal and they want to be attracted to the positive terminal. I can put a variety of things in my actual circuit, like light bulbs. So if I add light bulbs with series circuit, they ended up getting dimmer because I added more resistance in that circuit. So when you add more and more light bulbs in series, they got dimmer. The current is the same along that whole path. Same deal, since there's only one path, if one light goes out, they all go out. Whereas with parallel, they're all hooked individually to the battery, so they all have their own voltage, but the current got split because every time we had a new branch, every time we had a new path, the current of electrons would have to split into each path so that those electrons could go through there. If one resistor goes out, if that light bulb goes out, since there's other paths for the electrons to flow, they would just go through that other path. Okay? All right, that is it.